topic I'm going to cover now is called logistic regression, and it's used for classification modeling where the dependent variable is a nominal variable. Let's start with a simple example. This is a lost sales data set. It was provided by some distributor, and the variables are a status of an order. Was it in fact lost, or did they win the order? And there are three dimensions that might explain that. One is a quoted price for the order. These are in dollars. The days to delivery that were quoted in terms of how long it would take to deliver the order. And then there's two different part types, an original equipment or an aftermarket part. I'm not sure what kind of parts these are, whether they're automobile or something else. And what I've done is I've actually converted the nominal variable to a continuous one with a formula just to show you the wrong way to go about this analysis, because I think it is actually instructive that even doing it wrong, you actually do discover some useful information. So ignore the first column for now and just think about two variables: the time to delivery and whether or not an order is won or not, which I've right now coded as a numeric variable 0 and 1. So we could do fit y by x and say, do we win or lose the order on the basis of how long we're promising or offering delivery at? Because it's a 0-1 variable, because I've coded it that way and asked Jump to treat it as a continuous variable, just enlarge that a little. All you get are dots on two lines here. Jump is expecting continuous variable that the numbers could range anywhere in between 0 and 1, but we only have 0 and 1 values. Either the order was lost, 0, or 1, 1. And if you fit a line to this, the least squares regression line seems to be showing an inverse relationship, which would sort of make sense. The longer you say it's going to take to deliver, the less of the orders that you win, more of them you don't win, more zeros when you've got a longer time to deliver. Now, it's obvious why this is the wrong analysis. The red line seems to imply that you could lose, your lost order variable could be 0.4, when in fact it's all 0 and 1. It doesn't make sense to be talking about the numbers between 0 and 1, although in a minute we will talk about numbers like that. They do have a natural interpretation here. But down here in the range, let me see if I can get my pointer to work here. Preferences, laser pointer, okay. Down in this range, you're getting negative numbers for the y variable. Well, that doesn't make any sense. And if you extend this line far enough, it'll always have some values above 1. So what does it mean for the order 1 to be greater than 1 or less than 0? It doesn't mean anything. So this is not the right analysis. According to it, though, if you were to try to interpret it to say each extra day to delivery reduces something by some number 0.004, it is statistically significant. For that matter, we could investigate the other two variables. Does whether or not we win the order, is it affected by the price, and also by which part type? The second analysis I just did here has a continuous y variable and a nominal x variable, so it's going to actually do a one-way analysis of variance. This one, we just fit a line. Looks like a negative relationship, higher quotes, less something about the winning the quote, and this one you'll notice is here not significant, pretty high p-value. And in this case, the one-way analysis of variance does look like a significant difference between the aftermarket, where we are more where it seems like a higher value of winning the order than, or more orders won than on average than for original equipment. So just keep those in mind. I'll keep them up here somewhere. The reason the analysis is not right is that the y variable really is not continuous. The 0 and 1 just indicated whether it was won or lost, and we could change it to nominal, which would be correct, or I'll use the original column status because it's more descriptive. It actually just has 2 categories. The correct way to do this analysis would be to recognize that the y variable is in fact nominal. And let's do the original analysis here, time to delivery. You notice that the y variable nominal and the x variable continuous, we are in this left-hand box square, or logistic regression. And a logistic regression is a nonlinear relationship where we're going to fit an S-shaped curve, and the interpretation along this curve is going to be what happens to the probability of winning an order. That would be the natural interpretation of numbers between 0 and 1, that you're going to estimate the probability that you win an order. In fact, we're not going to estimate the probability directly. We're going to estimate something called the log of the odds ratio, which I'll get to in a minute. The language is quite subtle and confusing. But think of the y variable that we're trying to estimate is not really whether or not we win the order, but how likely it is that we win the order. Let's just conduct this analysis and see what you get. What you're seeing again is y values between 0 and 1. You're seeing a nonlinear relationship, and the interpretation is going to be for each of these points, we only have either the order is won or not won, but each of these points is going to indicate how long to the delivery and how likely it is that we will win this order as opposed to lose this order. And the negative slope line is basically showing that the longer the time to delivery, the less likely it is. This curve will never go below 0 and will never go above 1. It actually is an inverted S shape. It would have a positive S shape if longer time to delivery made it more likely that we would win the order. But this is an inverse relationship. The p-value being very low here basically says we can reject the hypothesis that there's no effect of the time to delivery on the odds of the likelihood of winning an order. I'll get to that language again here in a minute. And it has a significant impact. So speeding up delivery time would seem to improve our chances of winning an order. Let's just do the other 2 analyses here using the y variable as a nominal variable, and let's look at the quoted price for the part type. In the second of these, we have 2 nominal variables. We're going to get a contingency table. So the left-hand one, what we've gotten is we've gotten a logistic relationship. It looks linear here because, in fact, the inverted S shape is actually so flat that you can't tell that it's not linear, but it is not linear. And you also notice here the very high p-value. It's not a significant influence. This was 0.5293. Remember, back here, I think it was that one. The p-value was almost exactly the same thing. So that's my point about even if you didn't recognize that the y variable is nominal and you did the wrong analysis, which is linear regression here, it's not a linear relationship. You should not do linear regression. But in fact, you actually will get a quick snapshot of which variables are significant and the direction they take. There's a negative impact of the quoted price on probability of winning an order, but it's not statistically significant. Remember over here, we got that there was a significant difference and aftermarket was more likely that we win the order. And now over here, look at the row probabilities. If it's aftermarket, we have a 54% chance of winning the order. And if it's original equipment, it's only a 43% chance. And it is statistically significant with a chi-square test. So correctly recognizing that the winning or losing the order is a nominal variable, not continuous, we get the same qualitative results as if we wrongly did the analysis, treating the y variable as a continuous variable. My only point in pointing that out is that you don't want to do a continuous, you don't want to treat y as a continuous variable here, but that's one of the forgiving things about linear regression is even when the assumptions are not satisfied and it's not the correct analysis to do, you sort of get the right flavor of the results anyway. So I'll proceed with just these analyses because these are the correct ones to do. And of course, just like with any all the regression analysis we've looked at, looking at one variable at a time is instructive, but it's not really the right analysis to do. What you really want to do is take into account these all at the same time. So you would use the fit model platform. You would put the nominal variable as the y variable. And you notice the personality has changed to nominal logistic now. So with y as a nominal variable, the jump knows that you're looking at a categorical variable and it's going to use the logistic regression in the fit model platform. And you could include all, well, three of these variables, the price, quote, quoted time to delivery, and part type. If you have validation, you can put in that validation column. I'm going to leave validation out of it for now, but in fact, of course, you would normally want to include validation to see how good your model is and to help protect against overfitting. The best protection against overfitting here is you're choosing which variables to put in, and so you'll discover whether they seem to be significant or not, as opposed to asking the computer to go through all the variables and use whatever information it can get out of them, in which case overfitting becomes more likely because the computer will utilize, like a decision tree, it'll utilize as many cut points as it can to try to fit the data. So you run this nominal logistic, and the interpretation is pretty much the same as what we did in linear regression, except that the y variable is now a nominal variable. It's a nonlinear relationship we fit. It actually is estimating this thing, the log odds of won versus lost, and I'm going to get to that terminology here in a moment. You'll notice in terms of which variables matter and how much they matter. You look at the p-values here. The price quote is quite far from statistical significance. Time delivery is significant, and so is the part type. The quantitative influence of these is different now, and it's more accurate in the sense that each of these coefficients is taking into account the other variables at the same time. The interpretation of the numbers becomes more difficult because what's being estimated here as the y variable is not the probability of winning. It's the logarithm of an odds ratio of won versus lost. That is hard to interpret. So I'm going to get to that very shortly here. Okay, so to get to that, let's look at another data set, the Titanic data set. And this is to just get into, to straighten out the terminology of what the odds ratio means. These are all the passengers that were on the Titanic. There were also another 800 crew members, and here's details on each of the 1,313 passengers. I'm just going to focus on two variables right now: who survived and what gender they were. And this is simply a contingency table because they're both nominal variables. You run that contingency table, you find out for the females 66% survived, for the males only 17% survived. To get the terminology understandable here is a Word document that I posted, and this table that's shown here reproduces the numbers from the table we just saw in JUMP. It's the same numbers. So here are two ways to talk about these results. The odds ratio and relative risk. They both compare the likelihood of an event between two groups. So in this case, it's very clear a male passenger was much more likely to die than a female passenger. The question we're trying to answer now is some quantitative statement of how much more likely. The odds ratio compares the relative odds of death in each group. Odds are defined as the probability of something happening divided by the probability it doesn't happen. So for female, the odds were 1.96 to 1 against dying, because for females, 156 out of 156 divided by 463 was the probability of dying, whereas 307 divided by 463 is the probability of not dying. So the probability of dying divided by the probability of not dying gives you odds of 1.96 to 1. I think I switched. It's 1.96 to 1 against dying. So only 156 died, 307 survived. For males, the odds are almost 5 to 1 in favor of death. The probability of dying is 708 divided by 850. The 850 is going to be irrelevant because we're going to divide 708 divided by 850 by 142 divided by 850. You can ignore the totals. It's just 708 divided by 142, which is 4.99. So these two numbers, 0.51 and the 4.99, these are both considered odds. Odds are the ratio of the probability of something happening to not happening. The odds ratio is the ratio of the two odds. It has no units of measurement. There's no percent attached to it, no probability. It is ratio of two different things, both measured as the ratio of probability to the probability of not happening. So the odds ratio is actually 4.99 divided by 0.51, and it is accurate to make the concluding statement here. There's almost a 10-fold greater odds, 9.78, of death for males than for females. Now, I think if you ask people, it's almost a 10-fold greater odds of dying for males than females. Almost everybody understands you're saying males are far more likely to die than females. I think if you asked the average public how many of them could interpret exactly what 9.78 means, you'd be lucky to get 1 out of 100 people that could tell you that here. Because the 9.78 is actually the ratio of two odds. Each odds is a ratio of the probability of it happening, of dying to not dying. That's a very convoluted way of getting to that number. So when you see the log of an odds ratio, so we're not even talking about the odds ratio. When we look at JUMP, it's going to estimate the logarithm of the odds ratio. So logarithms are hard to interpret on their own right, and now it's a logarithm of an odds ratio. It's a very peculiar thing to try to talk about. A little more direct is to talk about the relative risk. It's also called the risk ratio. Compares directly the probability of death in each group rather than the odds. For females, the probability of death was 33.7%. For males, the probability is 83.3%, again referring to the numbers up in that table. So the relative risk of death is 2.5. 0.833 divided by 0.337. And it would be accurate to say there's 2.5 times the greater probability, there's 2.5 times greater probability of death for males than for females. Even then, we're only talking about the ratio of the probability for one group to the probability for the other group, although I think this one is a little bit closer to what people might be able to interpret. In the medical literature, there's actually fairly extensive literature on should you be using relative risk ratio, or should you be using an odds ratio? And it's not that one is necessarily better than the other. It depends on the purpose, the context, the actual numbers. In some cases, people advocate for using odds ratio, some cases risk ratio. The odds ratio is more common, I would say, but that's just by convention. They both have advantages and disadvantages. As you can see from this example, I think if you just look at the concluding statement, they don't have the same emotional impact on people. Somehow hearing a 10-fold greater odds of death for males and females sounds a lot more dramatic than 2.5 times greater probability of death for males and females. But in other circumstances, the numbers could work out differently, and it might seem more of an emotional impact to talk about the risk ratio than the odds ratio. So I think you can see that the terminology is somewhat confusing here, to put it mildly. The reason why the log of the odds ratio is what JUMP is focusing on is, and you can see in the book the derivation of the equations, I don't want to repeat them here, but basically by transforming it into the logarithm of the odds ratio, you are estimating a linear relationship between that y variable and the x variables. So it is a form of linear regression, except where the y variable is not just the probability of winning, it's this strange nonlinear thing, the odds ratio, the logarithm of the odds ratio. So the logarithm of the odds ratio turns out to be a linear function of what x variables you put into the model. So I don't need that one anymore. So if you now go back and look at the model we fit here, a key part to look at here when you look at the coefficients here and try to interpret them. I'm not going to try to interpret them directly, because what it's saying is if you increase the price quote by 1 unit, there is a minus 0.000193 change in the logarithm of the odds of winning versus losing. You can say that many times as you want. It's not going to sink in as making any sense. So what I would look at is first the sign here. What direction is the impact? Negative. Negative impact on what? On the logarithm of the odds of winning versus losing. In other words, there's a negative impact on the likelihood of winning. Higher prices, less likely to win the bid. That's the direction of change. That's intuitive. How much is the impact we'll get to in a minute? Is it statistically significant? Far from it. There's a negative impact of time to delivery on the odds of winning. So if you quote a longer time to delivery, you're less likely to win this bid or this job. And it is quite strongly significant. And if the part type is aftermarket, there is a positive and significant impact on the odds of winning. So you're more likely to win the job if it is an aftermarket part than if it's the original equipment part. If you want to see how large the impacts are, rather than try to estimate, to interpret these coefficients directly, what you should go to is the odds ratios. And for the odds ratios, let's take the part type first. That's the easier one. You're comparing two different groups, and they give you both comparisons, original equipment versus aftermarket or aftermarket versus original equipment. They're just inverses of each other. It's almost always easier to talk about the numbers that are greater than 1. So I'll focus on the second comparison here rather than the 1 divided by those numbers. And so what it's saying is the estimated odds ratio is 1.6. That's saying if it's an aftermarket part, you're about 1.6 times the odds of winning the bid as if it was an original equipment part. The confidence interval for that ranges from about 9% higher odds to 136% higher odds. So the odds ratio is from 9% higher to 136% higher odds of winning the bid if it's aftermarket. For a continuous variable like quote or time to delivery, you get an odds ratio, but you get 2 kinds, either a unit odds ratio, which is interpreted if there's a 1 unit increase. So a $1 increase changes the odds by 0.9999981. The confidence interval, you can see, ranges a very narrow interval. This is not unusual. It's often very hard to interpret unit odds ratios. Sometimes they're large enough numbers to actually make an interpretation, but often if the units of measurement cover sufficiently large values, prices vary quite a bit or time to delivery varies quite a bit, the impact of a 1 unit change is going to be very small, and so you almost never find a good interpretation of that. The range odds is a better shot, although sometimes they're a little too extreme. This is basically comparing the entire range of that value. So if you look at the price quote that was the highest price quote in the data set versus the lowest price quote, the odds ratio is 0.67, so it's about 33% less likely to, in terms of the odds ratio, odds ratio is 33% lower of winning the bid if you look at the highest quoted price versus the lowest quoted price. And the confidence interval, though, because it wasn't significant, is a huge range from 20% of the odds of winning it to 132% higher odds of winning it. Remember, it wasn't significant. We don't know if it's more likely or less likely to win the bid because of the price. Time to delivery, though, was significant, and you'll notice the whole range, the highest time to delivery, the odds are only about 3.4% of what the odds were, what the odds ratio is for the shortest time to delivery. Or put another way, if you look at the confidence interval for that, the odds are anywhere from it looks like 0.01 to 0.12, far more likely to win this order if the time to delivery is quoted at the low end, shortest time versus the longest time. Again, if there's a huge range, though, it's very hard to interpret, or kind of meaningless. You might have one outlier that's far longer than the others, and so this is just looking at the entire range, whereas the unit odds ratio is just looking at each particular unit. So often continuous variables, interpreting them this way doesn't really make a lot of sense. What I would suggest for continuous ones that make it much more concrete is to go to inverse prediction. And here what you do is you specify 2 of the 3 variables, leaving the other one out. So let's say we're talking about time to delivery, want to know how important that is. And we put in a price quote of, I think right now it's at the mean. So let's leave the mean value, 2780. It wasn't significant anyway. And let's look at an aftermarket part where you could change it to the original equipment. We'll do the aftermarket, and let's see what happens to the let's say we want to look at probabilities that range from 10%, 10 10% intervals, the probability of winning this job. So I'll go all the way from 10% to 80% chance of winning this. And what it's going to do, because I left out time to delivery, is tell me what time to delivery is associated with those probabilities. And you can see the confidence intervals displayed in this picture as well. That's what these horizontal lines are. You can see that the uncertainty range is larger for the longer delivery periods. But you can also see the point estimates here. Point estimates in the middle. So basically, you know, to get to a 70 or 80% chance of winning, you'd have to have a negative time to delivery. In other words, it's just not feasible it's not going to be feasible to get as high as a 70% chance of winning these jobs. But if you can only guarantee 85 days, you're estimated 30% chance of winning the bid. To get that to 40%, you'd have to reduce the time by about 24 days, from 85 to 61. So you can get very concrete, interpretable information from the inverse prediction. And that's what I would recommend doing certainly for a continuous variable. The other tool you can use to try to interpret the results is to go to the profiler. And the profiler will, just like it always does, it allows you to vary these, and you can see how the probability on the left of winning or losing the bid changes as you change and for categorical variables just from one to the other. So with 79.2 days and a price quote of 27.80, you would have a 23% chance of winning the job for the original equipment and a 32.5% chance for the aftermarket. So the profiler also will allow you to explore the impact of each of the variables. So let's look at another example. There's lost sales. This one was the subject of a fairly large lawsuit. You may remember a number of years ago that a bunch of Ford Explorers were involved in fatal crashes. And so this is the data for 2,321 fatal crashes in the state of California. And we have a cause. Was it a tire-related fatal crash or not? Let's just look at the descriptive information of that and the make of car. Very few of these crashes were tire-related. Only 27 out of 2,321, that's a little over 1%, were tire-related. And this is whether Ford was involved or some other car. And of course, Ford and I forget which tire manufacturer were involved in that suit, but they were the defendants in the lawsuit that people brought, that there was a problem with the Ford Explorer, and Ford Explorer said it was a problem with the tire manufacturer. So that's why the focus on Fords and tire-related fatal accidents. And you will notice that if you click on Fords, most of them were not tire-related. What happens if we just focus on the tire-related? I have to probably make this a little bit bigger. Yeah. Make this one a little bigger. Now you start to see something tire-related, which is a very small sliver. There is a little bit of a sliver here in the other. You can almost make it out, but notice how many of them were Fords. There does seem to be some kind of relationship here. If you just focus on those two variables, is tire related to which make of car it is, two nominal variables. It's a contingency analysis, chi-squared test if you like. Notice that you can see that visually there is a difference. A greater proportion of the Fords were involved in tire-related crashes than of other makes. If you look at the road percents here, it was 4% of the Fords were involved in tire-related fatal accidents, where it was 0.28% of the other brands. Highly significant p-value, so we basically would say it looks pretty likely that more Fords were involved in tire-related crashes. It's also feasible, though, that, and this is, of course, what Ford and tire manufacturer would argue, is there are other variables here that matter. How old was the car? And how many passengers were in it? Because some of these Ford Explorers had a lot more passengers than others. So let's just look at those two, just fit Y by X. Is it tire related? Is it related to each of these continuous variables? You'll notice from the p-values that both of these are significant. Both of them have a negative sign. Don't jump to conclusion the negative sign means it's less likely. To have to interpret the sign here that's shown in this, the sign here has to be interpreted in reference to what it's saying under the table. This is the logarithm of the odds ratio of it not being tire related. You could apply a value ordering if you wanted to tire related versus not tire related. I didn't do that, so Jump is putting it alphabetically. But for the odds of it not tire related versus tire related, a negative sign means that it's less likely that older cars would not be not tire related. In other words, it's more likely the older cars are tire related, which makes sense. That the older the car is, the more likely you'd have a tire related fatal crash. The more passengers that are in it, there's a negative sign associated again with the log odds that are not tire related. So the more passengers in, the more likely it is tire related. The double negative becomes a positive, which also makes sense. The more people you put in the car, the more pressure on the tires, the more likely it is it's tire related. You can clearly see the inverse S shape here. The reason that you only see sort of a little bit of it here is that the so few of the there's just very little variation. It is statistically significant, but very little variation as the vehicle age changes. For each of these, you could ask for odds ratios. And so, again, you have a unit odds ratio and an odds ratio. The second one, the range didn't print out, but the odds ratio over the range. They're generally for continuous variables. They're kind of hard to interpret each. The unit odds ratio is usually too small of an impact, and the range odds ratio would be too large. In any case, in the legal case here, it's not good enough to look at fit Y by X. What you really want to do is fit a model and try to explain the cause using all three of these. And actually, let's change the target to tire related. That should make it a little easier to interpret, because now you see the logarithm of tire versus non-tire. All three variables are statistically significant. They all have positive signs. So if it's a Ford, it is more likely to be tire related. The older the car is, the more likely it's to be tire related, and the more passengers in the car, the more likely to be tire related. So even though Ford and the tire company could appeal to the fact that it might have to do with the age of the cars and how many passengers were in it, both of those are true, but in fact, it's also true that even taking those into account, the Fords were far more likely to be tire related. How much more likely? Go to the odds ratios, and we would interpret this one right here. If it was a Ford, it was 17.5 times the odds of being in a tire-related crash than if it was a different make of car. That's a pretty dramatic difference. Can't remember how this lawsuit was decided, but if I had a guess, looking at this, my guess is they settled out of court. You really don't want this in front of a jury. And the confidence interval that's from 6 times the odds to 48.35 times the odds. Very large difference. Okay, I want to look at a different example in a little more detail now, just to show you how you evaluate the models more fully. So go back to the Pilgrim data, and we want to explain which customers we retain. I changed the types to be the correct types now. So you want to use data from 1999 to predict which customers were retained to the year 2000. Generally, you would want to use validation here, but I could create a validation column, but I'll leave that out of this because I want to make somewhat different points about this. Let's go ahead and fit a model. Retained is what we want to explain. As soon as I put that up, it's going to do a nominal logistic. And let's target those that are not retained. In other words, the lost customers. That's what you really want to be analyzing, is who do we lose? And you want to use all the 1999 variables. There's one more down here, whether or not they were using electronic bill pay. If you run the model, interpret the parameter estimates. It's in terms of the log odds of losing the customer. So a positive sign on a variable makes it, says as that variable goes up, it more likely will lose the customer. It's a negative sign, we're less likely to lose the customer. More profitable customers, we're less likely to lose them. And it's not quite statistically significant. So it's likely there's some correlation here, although it's not terribly strong. If they were not using online banking, positive sign means they are more likely that we will lose them. So we're less likely to lose the online banking customers. Notice bill pay is statistically significant. So the online banking was far from statistically significant. The bill pay is statistically significant and has a negative sign. So in fact, we are less likely to be, so when the bill pay is 0, so they weren't using electronic bill pay, we are less likely to have lost the customer. So those that used electronic bill pay are more likely to lose the customer, and it is statistically significant, which immediately raises 2 questions that business should ask themselves here is, are we losing the customers because the electronic bill pay doesn't work very well? So it's possible there's a flaw with that service. That's why we lose them. Or secondly, is it just a characteristic of the people that use electronic bill pay? In 1999, very few people used electronic bill pay. They may more likely to be the younger customers, ones that might be far more interested in exploring alternatives, and they might have been more prone to lose them because of their characteristics. It would be much harder to overcome that than a defective product. If the service didn't work right, that's something that presumably you can fix. You have more control over that than you do over the type of customer that is going to use electronic bill pay. There are some other significant variables here, age and income. They're category variables, but I've used them, they're numerically coded, so the higher numbers are older customers and the higher numbers for income are higher income customers. Both of them have negative signs, so that means that as they get higher, those numerically, we are less likely to lose the customers. We're more likely to retain higher income customers and older customers, and customers that were with the bank for a longer period of time. All of that is pretty good news, and they're all statistically significant. The districts, however, geographically is not a significant variable. Now, how good is this model? Well, we already know about the ROC curve. We could look at that. Focus on the lost customers. 0.61. It is better than random, but not much. It's not great. If you look at the lift curve, you focus on the 10% of the customers with the highest probability of not being retained, you get somewhere between 16 and 17% of the, here, 16 and 17% of the customers that you lose. That's not really a great lift. The confusion matrix, remember, it uses a 50% cutoff, so that is actually not that useful. Here it predicts virtually nobody would be retained. But that's because none of the probabilities reach 50% that we would lose the customer. It doesn't answer the question about whether the people that have a higher probability, estimated probability of loss, are more likely to be the ones that we lose. This just says none of them reach 50% probability of losing. You could use the add-in for how the different thresholds change the predictions, or actually there is a very quick way to get a view of that is to look at the ROC table, and it shows each of the probabilities, and it shows you the true negatives and the false negatives and false positives and true positives. So you get to see sort of the confusion matrix done in a matrix form here for each of these probabilities. If you were to use a probability cutoff, remember 50% is what's being used. Oh yeah, so if 50% is what's being used, the table doesn't go up past 24% because nobody in this data set had more than a 24% chance of being lost. At 24%, you notice that you get one estimated customer to be lost, and they're not even the one that you lose. But if you were to change this cutoff to something like, closer to 10%, faster to get to that. So at 10%, this is what it would basically look like. You would have gotten 3,700 of the true positives, no, 527 of the true positives, but 3,699 of the false positives. You get most of the true negatives because most customers you're predicting you would not lose. So you get almost all the ones you didn't lose, but 1,202 people you miss that you actually lose as customers. This is not a very good model, but there's a reason why it's not a very good model here. If you relaunch this analysis, and I wish this was the default, but you have to actually ask for this, you should click on informative missing. And the reason here is that, and you can see it showing in the data set, right? Click it, show it in the data set right behind here. You notice in the age column, see a lot of missing values. Also for income, a lot of missing values. We don't have ages and incomes for a lot of these people, and that could be significant, especially if this information is being collected voluntarily from customers. Many customers may not want to give their age or their income, and You could speculate that might be associated with your likelihood of keeping a customer. It's probably a trust issue. If they don't want to give their name and income, the bank, they may not trust this bank, and then they don't trust the bank, of course, we're going to be more likely to lose them. So if you click on informative missing here, rerun the analysis, notice a couple of things here. First of all, almost all the variables are statistically significant, which it wasn't true before. If you look at the confusion matrix, it is predicting that we will lose some customers, but again, this is based on a 50% cutoff. If you ask for the ROC curve, focused on not retaining, area under the curve is up to 0.78. That was up from 0.61. Much, much better model. If you look at the lift curve, targeting 10% of the people with the highest probability of losing the customer, you get about 30, looks like 33%, about a third of the customers that you actually lose would be targeted. So that's a pretty effective lift. What you should do when you have a model that you think is a reasonable model is you should go ahead and save the probability formula. When you do that, in the data set, you will get 4 additional columns. This column is actually the column that drives the results. It is actually has a formula, and it's a little bit messy. What it's doing is actually estimating the logarithm of the odds ratio. That's the dependent variable in this analysis, and it's a linear function of those x variables. So you've got the coefficients in this formula. This is what drives the results. Once you have the logarithm of the odds ratio, then it computes the probability for each person that they will be retained, that they won't be retained, and the most likely prediction, which is based on a 50% cutoff. Far more revealing than looking at that 50% cutoff, though, would be to compare what is the probability that we won't retain a customer and what actually happens. Interestingly, when you look at this left-hand picture, it's a bimodal distribution, which is promising in this case because we have a bimodal dependent variable. So if it turns out that down in this region where we have low probabilities of losing the customer, if those are the customers that we actually retained, and if these ones where we have a higher probability of losing the customer are the ones we didn't retain, then we'd have a pretty good model. You will notice that few of the probabilities in this model reach 50%, so you only have some outliers up here that have over a 50% chance. That's why it didn't predict we would lose too many customers, but there are some. Let's see who we lost. I see a bunch of points, all the highest probabilities of not retaining. We lost those. We lost a good chunk of the people in the 40 to 55% range. And we did lose some down here. These are ones our model's just unable to identify. Only a 5 or 10% chance that we would lose them according to the model, but we did lose them. But it suggests to me that if we used a cutoff somewhere on the order of around here, 40, a little over 40%, we're going to catch the vast majority of the customers that we actually lose. This model is doing a pretty good job discriminating between these two groups, but only when we've used informative missing. Before we used informative missing, the model didn't work very well. So in this case, identifying that missing data and using it in the analysis was actually quite important. So you do get the full array of tools that we looked at up to now. You do get profiler, so you can use a profiler to investigate the results. You do get inverse prediction, where you can specify all of the variables except for one, and then do inverse prediction and see how that variable, it's an alternative to the prediction profiler. It's another way of looking at focusing on a particular variable and how it influences the probability that you will retain a customer. So you could use prediction profiler, inverse prediction. You could also look at the ROC table and see how the performance, which is basically, these are the elements in the confusion matrix, how the performance changes with different cutoff probabilities. You could also use the add-in and produce the confusion matrix for a whole bunch of different cutoff probabilities. A lot of tools available. In terms of comparing it to decision trees, this is a different approach, because instead of asking the computer to search for different kinds of cutoff values and possibly use randomization in that by doing bootstrap forest or boosted tree, in this case, you're specifying what goes in the model. There is what would be called a probability model that underlies this, and that's that there is a linear relationship between the logarithm of the odds ratio and your x variables, and that the error term, the extent to which that does not fit the data perfectly, the error term is normally distributed, and that's what allows the analysis to produce things like p-values associated with these parameter estimates. So you'll notice that when you use decision trees, you don't get p-values. You do get contributions of columns, so it can compute in a decision tree how many of the branches of the tree use particular variables. In that sense, it's telling you their relative importance. But you can assess how likely it is that if you hypothesize that there's no effect of this variable, how likely it is that you would be wrong based on this evidence. Whereas with that probability model underlying this model, you actually get those p-values, and you get interpretations for each variable, that if you want to increase that variable by 1 unit, which is never the way you'd want to do it, you'd want to look at the odds ratios because they're easy to interpret. So focusing on bill pay, for instance, a bill pay customer, the odds of losing the customer is anywhere from 1.39 to anywhere from 39% higher to 137% higher. The point estimate is that they're 82% higher odds of losing the customer if they are an electronic bill pay customer than if they're not. And so you get odds ratios for all of the variables, which you don't get from the decision trees. So logistic regression, a very popular technique, gives you quite a lot of interpretable information. The one thing you would want to check, though, is it doing a better job than if you used a decision tree or a random forest. And we'll get to that after we add in a few more techniques that we can compare. So there's a number of techniques available for the classification modeling, but logistic regression is a very commonly used technique and really gives you quite a lot to interpret if you can get a model that's reasonable. This model seems to do a reasonably good job, whereas if we didn't use the informative missing, I'm not sure I would use that model for anything because it didn't give us very much in the way of results. So that is logistic regression.